this video, we're going to talk about a probability distribution where it's describing the actual population. Remember that we want to look at our samples and make inferences back about our population. And so when we're thinking about probability distributions, we can think that they are describing our population. At the same time, the probability histograms is like a histogram for a population. And so they are what's describing the population, and we can pull information from that. So looking at an example, here are the number of births, and this histogram represents the number of live births by a mother that is 50 to 54 years old who had a live birth in 2007. And so if they're having their first child at this age, they have a 0.313 frequency. If it's the second child that is this live birth, it's 0.244. If it's their third child, it's 165. Their fourth child, it's 0.099. If it's their fifth child at this point, it's 0.054. If it's their sixth child, it's 0.043. Their seventh child, it's 0.021. And if it's their eighth child, it's 0.061. So if you notice this histogram, it goes down for the most part, and then on the eighth child, it goes back up. So what this is saying is that more people in their between 50 and 54 have their first child at this point rather than their subsequent children, except for that eighth child that actually increases. And so we can make predictions and find the probabilities about a population based off of this histogram. And so looking at this, if I want the probability that a randomly selected person, 50 to 54-year-old woman who had a live birth in 2007, has her fourth live birth. So she would fit into this group. Maybe she wasn't necessarily one of these people, but we can make a prediction off of this. And we want to know the probability that it's the fourth live birth. So the probability that it's the fourth live birth is going to be right here, just this one, the probability that it's the fourth. So the probability that it's the fourth live birth is strictly going to be 0.099. Now, when we go to some of the others, and I'm going to scroll on down, and we're going to put this graph in down here, so that we can see it at different points. So what is the probability that a randomly selected 50 to 54-year-old mother who had a live birth in 2007 has her fifth or sixth live birth? So notice here we're wanting fifth or sixth. So we're wanting the probability that it's 5 or 6. So recall from our probability rules that that's the probability of 5 plus the probability of 6. And so the probability of 5 is 0.054, and the probability of 6 is 0.043. So the probability of 5 or 6 is going to be 0.097. So this means that a woman that is randomly selected between 50 and 54 who has a live birth in 2007, having her fifth or sixth child, is going to be a probability of 0.97. Okay, so continuing on, if we want to look at, and it came up here again for some reason, so let's move it down here. if we want to look at the probability that a randomly selected 50 to 54-year-old woman, our mother, who had a live birth in 2007, has had her 6 or more live birth. So this is the probability, 6 or more. So that would mean the probability of 6 plus the probability of 7 plus the probability of 8. So we want all 3 of these. So that's going to be 0.043 plus 0.021 plus 0.061. And that will give me 0.125. So the probability that it's the 6th or more live birth is going to be 0.125. So we can use these histograms. The height of them represents the probability to make predictions about a randomly selected person or item in that certain category. Now, continuing on with discrete random variables, we can also talk about the mean, variance, and standard deviation. So discussing the mean, it's still looking for the center, and what we're going to do is we're going to multiply each possible value by its probability, and then we're going to add the products. So what this looks like is, remember that the mean for the population had the symbol mu. Well, since we're talking about discrete variables, we're going to use mu sub x, subscript with an x down here, so that we know that it's not just the regular mean where we add them all up and divide. This one has a specific notation, mu sub x, and that's going to be the sum of all of the x's times their probabilities. So this is what the formula looks like for the mean. Now, the mean can also be denoted by E of x, which means expected value. It's just another name for the mean. So expected value of x is the exact same thing as the mean for a discrete random variable. So let's look at an example of finding the mean. A true-false quiz with 10 questions was given to a statistics class. Following is the probability distribution for the score of a randomly chosen student. Find the mean score. So what we're going to do to find the mean of this, we're going to take each of these and multiply the possibility the possible score times its probability. So I'm going to take 5 times 0.04 and add it to 6 times 0.16 plus 7 times 0.36 plus 8 times 0.24 plus 9 times 0.12 plus 10 times 0.08. So 5 times 0.04 is 0.2. 6 times 0.16 is 0.96. 7 times 0.36 is going to be 2.56. 8 times 0.24 is 1.92. 9 times 0.12 is 1.08. And 10 times 0.08 is going to be 0.8. If I add those all together, I get 7.48. So this student's mean score is a 7.5. Notice I rounded to 1 decimal place, and that is because our values are whole numbers. Remember our rounding rules. The mean is rounded to 1 decimal place more than what our x values are. So I rounded to 1 decimal place. So try some problems with probability distribution histograms and finding the mean of these probability distributions, and let me know if you have any questions.